Swayam Prabha. Digital India. Educated India.
So far we discussed the algorithm and using the search method, how to find out the shortest path and how to find out the tree and so on. We found out with the help of the graph theory ideas. Next we are going to continue the problem related to searching. So this talk describes one kind of goal based agent called problem solving agent. So already we understand the meaning of agent and how to find the environment based on the agent, how to we design the AI. Now we are mixing together goal based agent, call it as problem solving agent. So problem solving agent use atomic representation as described in the section, that is the states of the world are considered as wholes with no internal structure visible to the problem solving algorithm. So goal based agent that use more advanced factored or structured representation are usually called planning agents and are discussed. So we have to understand what is goal based agent. So planning is most important associated with the agent, then planning agent we can do that. So our discussion of a problem solving begins with a precise definition of problems and their solution and gives several examples to illustrate this definition, and we described several purpose search algorithm that can be used to solve these problems, and we will use several uninformed search algorithm that are given no information about the problem other than the definition. Although some of these algorithms can solve any solvable problem, none of them can do so efficiently. Informed search algorithm, on the other hand, can do quite well given some guidance on where to look for solutions. So this is the meaning of solving problem by searching. So in this talk we limit ourselves to simplest kind of task environment for which the solution to a problem is always a fixed sequence of the actions. The more general case where the agent future action may vary depending on the future percepts, and this talk uses the concept of asymptotic complexity, and that is denoted by order of that number or notation, and this is non-deterministic polynomial completeness, NP completeness, that is most important. Next, our problem solving agents goals help organize behavior by limiting the objectives that the agent is trying to achieve and hence the action it needs to consider. So the goal formulation based on the current situation and the agent performance measure is the first step in problem solving. So the problem formulation is the process of deciding what action and states to consider a given goal, and we discuss this process in more detail later. For now Let us assume that the agent will consider action at the level of driving from one major town to another. So, each state therefore corresponding to being in a particular town. In general, an agent with several immediate options of the unknown value can decide what to do by first examining future action that eventually lead to states of known value. So, this is things for framing a problem. So, action is most important and certain consideration is important, and what goal is also most important, so that we can discuss more about that framing a problem. So, we assume the environment is observable. So, the agent always knows the current state. For the agent driving in Romania, it is reasonable to suppose that each city on the map has a sign indicating its presence of arriving drivers. So, we also assume that environment is discrete. So, at any given state, there are only finitely many actions to choose from. So, this is true for navigating in Romania, because each city is connected to smaller number of the other cities. So, we will assume that the environment is known. So, the agent knows which states are reached by action. So, having an accurate map suffices to meet the condition for navigation problems. Finally, we assume that the environment is deterministic. So, each action has exactly outcome. Under the ideal conditions, this is true for the agent in Romania. So, the process of looking a sequence of action that reaches the goal is called search. So, we have to go for search algorithm, takes a problem as input and returns a solution in the form of action sequence. Once a solution is found, the action is recommends, can be carried out. This is called execution phase. So, we have a simple formulate, search, execute, design for the agent as shown in the figure after formulating a goal and a problem to solve. When choosing an action, because it knows in advance what they will be. So, an agent that carries out its plans with its eyes closed so as to speak must be the quiet certain of what is going on. So, control theorists call this an open loop system, because ignoring the percepts breaks the loop between agent and environment. Next, well defined problem and solution. A problem can be defined formally 5 components. One is the initial state the agent starts in. For example, the initial state for our agent in Romania must be described in as in INARD. This is inbuilt. So, a description of these possible action available to the agent. Next is action. First one is initial state, next is possible action available to the agent. Next, given a particular action of S, return to set action that can be executed in S. We say that each of these action is applicable in S. So, next one is applicable. So, for example, from the state in ARD, the applicable action are go SIBIU Sibiu, go Timisoara and go Zernin. So, these are all the action initial state to applicable, and the description of which action does, the formal name for this is the transition model. Fourth one is transition model, and specified by a function result of S comma A that returns the state that result from doing action A in state S. We also use the term successor to refer any state reachable from a given state by a single action. For example, we have a result in ARD go Zerind is equal to in Zerind. So, this is the meaning of well defined problem corresponding we have a solution. Now, we have a inbuilt form of solving agent. First, function simple problem solving agent percept returns an action, and persistent the sequence SEQ and action sequence initially empty, state some description of the current world state, goal a goal is initially null, problem a problem is a formulation. Now, state update state comma percept. If SEQ is empty, then goal and formulate goal state. Next problem formulate problem of state comma goal, and then sequence is a search problem. If sequence is a failure, then return a null action, the first of sequence, rest of sequence, and return action. So, this is the inbuilt program we have to do. A simple problem solving agent first formulate a goal and a problem for searches for a sequence of action that would solve the problem, and then execute the action on a time. When this is complete, it formulates another goal and starts over. Now, so once you understood this inbuilt function and a simple problem solving agent, it first formulates a goal and a problem search for a sequence of action that would solve the problem, and then execute the action one at a time. When this is complete, it formulates another goal and starts over. That is the meaning of the function of a simple problem solving agent, and returns an action. Then persistent is a sequence in action sequence initially empty, state some description of the current world state, goal a goal initially null, and problem a problem formulation. State update the state, that is within bracket state comma percept. Next statement is if sequence is empty, then goal formulate goal within bracket state, problem formulate problem within bracket state comma goal. SEQ is a search problem, and then if SEQ is equal to failure, then return a null action, first of sequence, rest of sequence, and return actions. So, this is a simple problem solving agent. Now, together the initial state action, the transition model implicitly define the state space of the problem. So, the set of all state reachable from the initial state by a sequence of action. The state space forms a direct network or graph in which the nodes are states and the links between the nodes are action. So, the map of Riemannia shown in the figure 3.2 can be interpreted as a state space graph. If we view each road as a standing for two driving action, one in each direction. So, a path in the state space is a sequence of states connected by a sequence of action. Next, the goal test, which determines whether a given state is a goal state. Sometimes there is an explicit set of possible goal states, and the test simply checks whether the given state is one of them, and the agent's goal in the Riemannia is a singleton set of set bracket in of BUCHA or rest, Bucharest is one of the function we have to use in the Romania, and we have a map, the part of the Romania. So, here you can start with anywhere, and then we can easily find out the road map, and then Oradea starts and Zerind 71 kilometers like that, and Zerind to Arad 75. From Oradea to Sibiu is 151. From Arad to Sibiu is 140. So, if you find out the path from Oradea to Sibiu or Arad to Sibiu, whichever is lesser, that you have to find out. But Zerint you can go from Zerint to Oradea and move to Sibiu, or Zerint to Arad, Arad to Sibiu you have to go. So, which one is the shortest? So, we have to use the search algorithm, and the shortest path we can determine from this to that. Like that we have a network, right. So, we need a graph theoretical approach of this, or we have to find out the PERT, project evaluation review technique, using the longest path minimum time required we have to find out, that is optimized. So, this is the structure Timizoro, Lugoji and Megadia, Drebota, Craiova, Rumunisigo, Vilasia, Sibiu, Fagras, Pitesti, Bucharest, Uzianinsi, Vasuli, Yasi and Niamt. So, this path you have to find out, and we have to search which is the longest path with the minimum duration of the time, and finding the optimum ideas. So, we need a agent, and based on the environment, then take the taxi drive, and then with the help of the AI, and we can use the one source to sink, we can move. So, this sometimes the goal is specified by the abstract property rather than the explicit enumeration of states. For example, in chess, the goal is to reach to state called checkmate, where the opponent is king is under attack and cannot escape. So, every one of you know how to play the chess board and how to win a game, and that you have to form the program. Next is the path cost function that assign a numeric cost to each path. So, the problem solving agent chooses a cost function that reflects its own performance measure. For the agent trying to go to the Bucharest, time is of the essence. So, the cost of path might be its length in kilometers. So, in this talk we assume that the cost of the path can be described as a sum of the cost in the individual action along the path. So, the step cost of taking action A in state, S to reach the state, S dash denoted by C of S comma A comma S dash. So, the step cost of Romania are shown in the figure as route distance. We assume that the step costs are non-negative. So, the preceding elements define a problem and can be gathered into a single data structure that is given as input to a problem solving algorithm. So, a solution to a problem is an action sequence that leads from the initial state to the goal state. A solution quality is measured by the path cost function, and optimal solution has the lowest path cost among all solutions. So, in the preceding section, we proposed the formulation of the problem, getting to Bucharest in the term of the initial state action transition model, goal, test and pathcast. So, this formulation seems reasonable, but it is still model. So, an abstract mathematical description and not the real thing. Compare the simple state description we have chosen in ARAD to an actual cross country trip where the state of the world includes so many things: the traveling companies, the current radio program, the scenario of the window, the proximity of law enforcement officers, the distance to the next stop, so the condition of the road, the weather and so on. All these considerations are left out of our state description because they are irrelevant to the problem of finding a route Bucharest. So, the process of removing detail from a representation is called abstraction. In addition to abstracting the state description, we must abstract the action themselves. So, the driving action has many effects. Besides changing the location of the vehicle and its occupant, it takes up the time, consumes fuels, generates pollution and changes the agent, as they say travel in broadcasting. So, our formulation takes into account only the change in location. Also, there are many actions that we omit altogether: turning on the radio, looking out of the window, slowing down for the law enforcement officer and so on. So, these are all the formulation. Of course, we do not specify the action at the level, the turn steering wheel to the left by 1 degree. So, can we be more precise about defining the appropriate level of abstraction? So, think of the abstract states and action we have chosen as a corresponding to large set of detailed world states and detailed action sequences. Now, consider a solution of the abstract problem. For example, the path from Arad to Sibiu to Rubinku, Vilesia to Pitasti to Bucharest. So, this abstract solution corresponds to large number of more detailed paths. For example, we could drive a solution corresponding to large number of more detailed paths. We could drive the radio on between the Sibiu and Rubinku, Vilesia and then switch it off for the rest of the trip. So, the abstraction is valid. If we expand any abstract solution into a solution in the more detailed world, a sufficient condition is that for every detailed states, that is in ARAD is Arad, there is a detailed path to some state, that is in Sibiu and so on. So, the abstraction is useful if carrying out each of the action in the solution is easier than the original problem. So, in this case, they are easy enough that they can be carried out without further search or planning by an average driving agent. So, the choice of the good abstraction thus involves removing as much detail as possible while retaining validity and ensuring that the abstraction action are easy to carry out. So, were it not for the ability to construct useful abstraction, intelligent agents would be completely swamped by the real world. Now, this problem solving approach has been applied to vast array of task environment. We list some of the best known here, distinguishing between the toy and a real world problem. A toy problem is intended to illustrate or exercise various problem solving methods. It can be given a concise extract description and hence is usable by different researchers to compare the performance algorithm. So, a real world problem is one whose solution people actually care about. Such problems tend not to have a single agreed upon the description, but we can give the general flavor of their formulation. So, this is the the state space for the vacuum world, S for the suck, R for the right, L for the left, and we have a vacuum cleaner, and it will first demonstrate it from here, and then it moves to the left, search it, and that environment having a dust, then it will suck. So, the environment will be the square, rectangular, whatever may be, it first check with the help of the sensor, it moves and then moves to the right, and the same way check, and then once again it will move to the right and then go to the left. So, it will move to what this technique, and the possibilities of first check to the sucking of the matter to the left to the sucking of the right, and then right to the left it goes, and then we can have a link like this. So, this is the state space. So, different state space we can occur. One is left and one is another is right, and then it moves left and right, and finally the path they created, and based on the agent and environment it will act it. It will act. Now, we have a toy problem. The first example we examine the vacuum world. First introduced in this talk, this can be formulated as a problem as follows: states. The state is determined by both the agent location and the dirt locations. The agent is one of the two locations, each of which might or might not contain dirt. Thus, there are 2 into 2 square equal to 8 possible world states comes. So, this is the 8 possible state space come. So, 1, 2, 3, 4, 5, 6, 7, 8. Now, the large environment with n location as n into 2 power n states. So, the initial state, any state can be designated as initial state. Action, in this simple environment, the state has just 3 action, one is left, right and suck. So, the larger environment might also be include up and down. Next, transition model, the action have their expected effects. Expect that moving left in the leftmost square, moving right in the rightmost square, and sucking in the clean square have no effect. So, the complete the state space is shown in the figure 3.3. So, the next goal test, this check whether all the squares are clean, and next next test is a path cast. Each step cost 1. So, the path cost is number of steps in the path. This is the meaning of toy problems. So, next compared with the real world, the toy problem has a discrete location, discrete dirt, a reliable cleaning, and it never gets any dirtier. So, this relaxes some of these assumption. Next, 8 puzzle, an instance of which is shown in the figure 3.4, a typical instance of 8 puzzle. So, this figure consists of 3 cross 3 board with the 8 numbered tiles and a blank space. Because of the tile is adjacent to the blank space, can slide into the space. So, this object to reach a specified goal state, such as one shown on the right of the figure. So, the standard formulation is as follows. So, this is a way we can move. So, first you move to 3 and bring 1, like that it goes like that, and you started with the sequence pattern 1, 2, 3, 4, 5, 6, 7, 8. So, this way we have to reach the goal. So, according to the one open, that is a free blank space is required, and then move from right to left, left to right, like that we have to do that. So, here what we require, the state is describes specifies the location of the each of the 8 tiles and the blank in one of the 9 squares. So, the initial state, any state can be designated as a limit state. Note that any given goal can be reached from exactly half of the possible initial state. So, action, the simplest formulation defines the action as a movement of the blank space left, right, up or down, and different subsets of these are possible depending on whether the blank is. And next one is a transition model. Given a state and action, this returns the resulting state. For example, if we apply left to the start state in figure, the resulting state as a phi and the blank is switched. Next to goal test, this checks whether the state matches the goal configuration shown in the figure. And path cost, each step cost is 1. So, the path cost is the number of steps in the path. So, the 8 puzzle belongs to the family of sliding block puzzles, which are often used as test problem for a new search algorithm in AI. So, this family is known as NP complete. So, one does not expect to find a method significantly better in the worst case than the search algorithm and described in this talk and the next. So, the 8 puzzle has 9 factorial by 2 equal to 181,440 reachable states and is easily solved. In the 15 puzzle is a 4x4 board, has around 1.3 trillion states, and random instance can be solved optimally in a few milliseconds by the best search algorithm. The 24 puzzle is a 5x5 board, has around 10 power 25 states, and random instances take several hours to solve the optimality. So, the goal of the 8 square queens problem, I hope all of you know, in the chessboard, and taking the 8 queen, and is it possible to place the 8 queen on the chessboard such as no queen attack any other. So, a queen attacks any pieces in the same row, column or diagonal. For example, you take this one, does not attack 2, does not attack 3, does not attack 4, does not attack 5, does not attack. Now, if you place anywhere here, the problem will come. You check it out, and then here it does not affect. Okay. Suppose if you place the queen here, right, and it does not intersect one another, and if you have a queen here, it does not affect. If you have a queen, it does not affect. But if you place that in the cross, it will affect. So, the solution you have to think about and do it yourself. But although the efficient special purpose algorithm exists for this problem, and for the whole n queen family, it remains a useful test problem for a searching algorithm. So, there are two main kinds of formulation. An incremental formulation involves operators that augment that state description, starting with the empty state for the 8 queen problems. This means that each action adds a queen to the state. A complete state formulation starts with all the queen on the board and moves them around. In either case, the path cost is of no interest because only the final state counts. So, the first increment formulation one might try is the following. Number 1, states any arrangement of 0 to 8 queen on the board is a state. So, initial state, no queens on the board. Action, add a queen to any empty square. Next, transition model returns the board with the queen added to the specified square. Goal test, 8 queens are on the board, none attacked. So, in this formulation we have 64 into 63 into 57 is approximately equal to 1.8 into 10 power 14 possible sequences to investigate. So, a better formulation would prohibit the placing of a queen in any square that is already attacked, and we have a states all possible arrangement of n queens where n varies from 0 to 8, one per column in the leftmost n column with no queen attacking another action. Add a queen to any square in the leftmost empty column such that it is not attacked by any other queen. So, this formulation reduces to 8 queen state space from 1.8 to 10 power 14 to just 2057, and a solution are easy to find. On the other hand, for 100 queens in the reduction is roughly 10 power 400 states to about 10 power 52 states, a big improvement, but not enough to make the problem tractable, and this describes in the complete state formulation and also gives a simple algorithm that solve even a million queens problem with easy. Now, our final toy problem was derived by Donald Knuth and illustrated how infinite state space can arise. Knuth conjectured that starting with the number 4, a sequence of factorial square root and floor operation will reach any desired positive integer. For example, we can reach 5 from 4 as follows: root of 4 factorial, root of 4 factorials, and it reaches 5 of the ceiling. So, that the problem defines a very simple state is positive numbers. So, initial state is 4, action is applying factorial and square root and floor operation, factorial for integer only. Transition model is given by the mathematical definition of the operation, and goal test state is the desired positive integer. To our knowledge, there is no bound on how large number might be constructed in the process of reaching a given target. For example, the number 6204484not17332394393C600000 is generated in the expression for 5, so that the space for the problem is infinite. Such a state space arise frequently in tasks involving generation of mathematical expressions, circuits, proofs, programs, and other recursively defined objectives. So, we have already seen how the root finding problem is defined in terms of a specified location and transition along links between them, and root finding problem algorithm are used in the variety of application, some such as a website and in car system that provides a driving direction and a relatively straightforward extension of the Romania example. Others such as routing video streams in computer networks and military operation planning and airline travel planning system, and involve much more complex specification. So, consider the airline travel problem that must be solved by travel planning website. So, the states are, each state is obviously includes a location, for example, an airport, the current time. Furthermore, because the cost of action, a flight segment may depend on previous segment, their phase basis and the status as a domestic or international, the state must record extra information about these historical aspects. Next, initial state, this is specified by the user's query, and next one is the action. Take any flight from the current location in any seat class, leaving after the current time, leaving enough time for within airport transfer if needed. Next, transition model, the state resulting from taking a flight will have the flight's destination as the current location and flight arrival as the current time. Then the goal test, are we at the final destination specified by the user? Then path cost, this depends on monetary cost, waiting time, flight time, customs and immigration procedure, seat quality, time of day, type of airplane, frequently flyer mileage, awards and so on. So, these are all the path cost. So, this is the real world problem for finding the root. So, commercial travel advice system use the problem formulation of this kind with many additional complication to handle the Byzantine fare structures that airline impose. Any seasoned traveler knows how that not all travel goes according to plan. A really good system should include contingency plans such as backup reservation on alternate flights to the extent that these are justified by the cost and likelihood of failure of the original plan. So, touring problem are closely related to route finding problem, but with an important difference. Consider for example, the problem visit every city in figure 3.2 at least once, starting and ending to Bucharest. As with the route finding, the action corresponding the trip between adjacent cities. The state space however is quite different. Each state must include not just the current location, but also set of cities the agent has visited. So, the initial state would be in Bucharest, visited Bucharest. A typical intermediate state would be in Vaslui, visited the Bucharest and Uziansi, Vaslui, and the goal test would check whether the agent is Bucharest and all the 20 cities have been visited. So, this is a technique we have to do that. Next one is a travelling salesman problem, is a touring problem in which each city must be visited exactly once. The aim is to find the shortest tour. So, the problem is known to be NP hard, but enormous amount of effort has been expanded to improve the capabilities of travelling salesman algorithm. In addition to planning trips for travelling salespersons, these algorithms have been used for tasks such as planning movement of automatic circuit board drills and of stocking missions on shop floor. So, this problem already we discussed in the graph theory, and same thing we have to apply here and finding this shortest tour. So, a VLSI layout problem requires positioning millions of components and connection on a chip to minimize area, minimize circuit delays, minimize tray capacitance and maximize manufacturing yield. So, the layout problem comes after the logical design phase and is usually split into two parts. One is cell layout and another is a channel routing. In cell layout, the primitive components of a circuit are grouped into cells, each of which performs some recognized function, and each cell has a fixed footprint based on the size and shape and requires a certain number of connection to each of the other cells. So, the aim is to place the cells on the chip so that they do not overlap and so that there is a room for connecting wires to be placed between the cells. So, the channel routing finds a specific route for each wire through the gaps between the cells. So, these search problems are extremely complex, but definitely worth solving, and later this ideas we present some algorithm capable of solving them. Next, robot navigation is a generalization of the route finding problem and described earlier. Rather than the following a discrete set of routes, a robot can move in a continuous space with an infinite set of possible action and states. For a circular robot moving on a flat surface, the space is essentially two-dimensional. When the robot has arms and legs or wheels, then must also controlled. The search space becomes a many-dimensional. Advanced techniques are required just to make the search space finite. And also we examine some of these methods in this book. In addition to complexity of the problem, a real robot must also deal with errors in their sensor reading and motor controls. So, next is automatic assembly sequencing of a complex object by robot was the first demonstrated by Freddy. A progress since then has been slow but sure to the point where the assembly of intricate objects such as electric motors is economically feasible. In assembly problem, the aims to find an order in which to assemble these parts of some object. If the wrong order is chosen, there will be no way to add some part later in the sequence without undoing some of the work already done. Checking a step in the sequence for feasibility in a difficult geometrical search problem closely related to robot navigation. Thus, the generation of legal action is an expensive part of the assembly sequencing. So, any practical algorithm must be avoid exploring all but a tiny friction of the state space. So, another important assembly problem is a protein design, in which the goal is to find the sequence of amino acid that will fold into a 3-dimensional protein with the right properties to cure some disease. Thank you.